Hi, this is Brooke Hollingshead with Math 510 Applied Linear Algebra. This is video presentation number 4 about quadratic forms. So what we're going to do in this video is take a quadratic form of a polynomial and diagonalize it and put it into a form using eigen coordinates so that it is a little bit easier to look at it and tell what it's going to look like geometrically and be able to get some information from it. So we're going to start by finding a matrix A so that we can multiply the vector xyz transpose by A by the vector again and get out our quadratic form that we are starting with. So the first thing we're going to do to use this formula is we're going to go ahead and start with xyz, and then this is going to be our matrix A, and we're not quite sure what it is yet, and xyz. And the way that we're going to do this is our x squared coefficient and our y squared coefficient and our z squared coefficients are going to be our diagonals. So we just have 1 for x squared, 1 for y squared, and 7 for z squared on our diagonals. And then our top term and our left middle term are going to be what make our xy. And since it's 4, then we can put a 2 and a 2, and that'll make our 4. And now we're done as far as our quadratic form goes. So the rest of them can just be zeros, and that is going to turn out really handy for us later. So this actually is our matrix A. Then I'm going to take this and go ahead and figure out my eigenvalues and eigenvectors. So to do that, we take the determinant of that matrix, subtracting the lambda I. So 1 minus lambda, it's only going to be, because it's I, it's only on the diagonals. So 1 minus lambda and 7 minus lambda. And this, like I said, is going to turn out real handy for us because we've got zeros above and next to. So all I have to do for this determinant is take 7 minus lambda and figure out the determinant of this box that's left over, and then I'm done because the rest are zeros. So I have 1 minus lambda, 1 minus lambda, minus 4. So when I multiply these out, I get 1 minus 2 lambda plus lambda squared minus 4. So I'm going to leave this. I'm not going to multiply it out because it's going to end up being able to factor for us very nicely. Minus 3. And so 7 minus lambda, I can factor this back out, lambda minus 3 and lambda plus 1. And that gives us our eigenvalues of 7, 3, and negative 1. So to figure out our eigenvectors, we plug these in. So for lambda equals 7, we plug in a minus lambda I times our vector equals the 0 vector. And I'm only going to do it for eigenvalue 7 just to save time. So I'll walk us through that one. So we have a minus 7i. So I'm subtracting 7 on the diagonals basically. So negative 6, and 0. Then we put this in reduced row echelon form. And for this one, I have to get multiplied by the vector v equals the 0 vector. So when I multiply these out, I get that x equals 0, that y equals 0, that z is a free variable. And to make my life simpler, I'm going to choose to have that one be 1. So 0, 0, 1 is my first eigenvector for eigenvalue of 7. So I can go back for the other ones for eigenvalue of 3. Excuse me, my eigenvector is going to be 1, 1, 0. And what I can do, I don't need to worry about it here because this art is already only a length of 1. But for these guys, if I want to normalize them, I'm going to have to go ahead and divide by their length. So square root of 1 squared, 1 squared, and 0 squared. So this is going to be square root of 2 to make this into an orthonormal vector. To normalize it, I just divide out its length so that the length becomes 1. So same thing for -1. I can tell you what my vector is already -1, 1, 0. And then the same thing to normalize it. I'm going to divide it by -1 squared, 1 squared, and 0 squared all together. The length is going to be square root of 2 then. Okay, so there's my eigenvalues. There's my eigenvectors that go with that. Using that, very handy, I can now come up with a quadratic form for using the eigencoordinates. And what this looks like is just using my lambdas multiplied by my vectors. Squared. So my first lambda was 7. My second lambda was 3. My third lambda was -1. So this is going to be my equation using eigencoordinates. And what's really nice about this is I don't have that extra term in this one to look at it to tell what it's going to be geometrically. So I can look at this, and if I had the equation xyz equal to 1, well, I can use this with the bars, and I can say, oh, if I look at the way that this form looks, and I have that -z squared term, and it's equal to 1, I know that this is going to be a hyperboloid of one sheet that is going to be rotated. Okay, so this is going to kind of look like, this is going to be an absolutely awful drawing, especially because it's not accurate, but essentially a hyperboloid of one sheet has what kind of looks like two cones that are connected in the middle, and it's going to be rotated. And I could tell that if I graphed the original equation, but because we were able to use the diagonal form and therefore go in and use this formula and use our eigenvalues, we can see it a lot easier without having the extra terms. Okay, thank you.